Hello everyone and welcome back to the another class of fundamentals of particle and fluid solid processing. We were discussing about the transport of liquid solid system, that is the slurry transport, and we have introduced this yield stress models in the last class. So in the yield stress models we mentioned that we can have Bingham plastic, Herschel-Berkeley or the yield power law models. Now say for the time being we focus on this Bingham plastic and the Herschel-Berkeley. So this Bingham plastic, as it shows that it behaves as if a Newtonian liquid with a shear stress, with a yield stress. So this yield stress, if it is tau y, the expression of the shear stress for Bingham plastic becomes tau y, which is the yield stress, plus mu p and the shear rate. And in case of Herschel-Berkeley, it is the component that we have seen for the power law plus the shear stress, the yield stress. So in this case, that means in Bingham plastic, the slope of this straight line gives a viscosity measurement. That viscosity in Newtonian case we have mentioned that is an absolute viscosity of the dynamic viscosity, but in this case we call this as a plastic viscosity. Now so if we now look into the Bingham plastic model, this is the expression where this plastic viscosity is expressed as tau minus tau y divided by gamma dot, which is the strain rate. Now in case of Bingham fluid, the apparent viscosity, which is defined as tau, the shear stress by the shear rate, becomes plastic viscosity plus this component. This comes from these two expressions. The combination of these two results in the calculation of apparent viscosity in case of Bingham fluid, because this apparent viscosity is what we will be needing in future calculations, again to calculate say the Reynolds number, because that is required for the friction factor calculation, which helps us in calculating the pressure drop. So that is why at first we have defined what is the apparent viscosity in case of Bingham plastic. Similarly, for the Herschel-Berkeley model, we have this expression. If we separate, because we now understand that this is the power law component and this is the yield stress component. So in this case, similar to this derivation, the apparent viscosity becomes this expression. And we can understand that if n becomes 1, then earlier the power law fluid was falling back to the Newtonian case. Now in this case the Herschel-Berkeley falls back to the Newtonian level with a shear rate, with the yield stress, which is again the Bingham plastic. So here if we put n is 1, this becomes once again this expression. Because the K becomes mu p, the plastic viscosity. So Bingham plastic is basically the one extreme of Herschel-Berkeley model or one variation of the Herschel-Berkeley model. Now, this shape of the velocity profile in this yield stress model is not simple as it was in the case of power law rheology. So, here this is the schematic. It shows a typical velocity profile when it flows through a horizontal pipe. So, this is our axial direction, this is the radial direction, and we see that there is a zone of r star to the radius, the radial distance 0. In this zone, we see there is a flat velocity profile. The gradient of the velocity in this direction is 0. And in this zone, we see the shear stress is less than the yield stress. And outer of this region, we see the shear stress is greater than the yield stress. And that is the reason it takes this kind of a shape. And at the wall, we have tau 0, which is the shear stress at the wall of this value. Now, this is a typical velocity profile that has been seen from its theoretical derivation in case of this yield stress models. Now, if we focus on the Bingham plastic rheology, and again we try to find out what is the pressure drop in such slurries that will exhibit this Bingham plastic behavior. So, in fully developed flow condition, it has been seen that the average velocity has this expression, or it varies in this manner, where once again tau y is the yield stress, tau 0 is the shear stress at the wall, r is the radius of the pipe, mu p is the plastic viscosity. Now, when this ratio, that is tau y by tau 0, is much less than 1, then this expression can be simplified to only having this part. You can neglect this tau y by tau 0 components. So, once this average velocity of the flow is known, okay, we can again have it rearranged for the del P calculation or del P by L calculation, the pressure drop per unit length calculation. If we write the tau 0 in terms of del P, writing tau 0 in terms of del P, we have seen this expression at the wall. So, if we do that, we find that del P by L has an expression of this, and this is the expression for Bingham plastic rheology. And interestingly, if we see in this expression that yield stress is 0, which means this becomes a Newtonian fluid, and it should fall back to the eigenpartial equation, because this part is then gone. Because tau y is 0. So, it falls back to the Newtonian liquid pressure drop calculation. So, the expression for Bingham plastic pressure drop calculation in laminar flow is this one that you have to remember. In turbulent flow, which means we have to again check what is the Reynolds number. Now, in this case, this regime transition for the Bingham plastic depends on these two dimensionless numbers. One is the Reynolds number as well as the Hedstrom number, which is He. Now, this number, Hedstrom number, is the product of Reynolds number and the ratio of internal strain property to the prevailing shear strain condition, that is this quantity divided by this quantity multiplied by Re. That gives this expression. So, that means the flow condition is dependent on these numbers, or these numbers would help us to determine whether the flow is in laminar or in turbulent condition. So, quite naturally we have to have a flow regime chart. Now, in this case, this flow regime, the friction factor chart is dependent on the Reynolds number as well as the Hedstrom number. So, these are the Hedstrom number lines, and the x axis is the Reynolds number, y axis is the friction factor, both are in log scale. We know this expression for calculation of del P. So, both these, that means this chart and this expression, will help us to determine what is del P for the liquid or the slurries that is behaving as Bingham plastic. So, this line is what is for the Newtonian liquid or the Newtonian fluid in turbulent condition. This is what was for laminar condition 16 by Re. But depending on these two numbers, that is the Reynolds number and Hedstrom number, we can find out what is the friction factor, and then we can find out what is the del P. So, this is how we calculate the pressure drop requirement for a slurry that is showing Bingham plastic behavior, and accordingly we can understand its pumping cost. Now, this transition Reynolds number here also we have to look into, and in this case this transition Reynolds number is dependent on this Hedstrom number with this kind of an empirical correlation. So, based on this Hedstrom number, you can find out what would be the transition Reynolds number for that flow, and then you judge whether that Bingham plastic flow is having laminar condition or turbulent condition. So, basically we have to find out what is the Hedstrom number of this Bingham plastic flow, then we look into its transition Reynolds number from this empirical relation. Once we know that, we also calculate what is the Reynolds number for this Bingham plastic from this relation, because here it is the mixture density and the plastic viscosity is what it involved in the calculation. So, you can easily calculate that provided these two informations are known. Once these two Reynolds numbers are known, then we look into this chart and find out what is the friction factor. Now, this was the discussion on the homogeneous slurries, that is, we thought or we assume that the particles are not settling, it is suspended till the flow, all the flow happens, all the slurry flows from one place to other place. But in case of heterogeneous slurries, we know its nature, that few particles will tend to settle, but it will settle in the saltation regime. So, in heterogeneous slurries, as there is a concentration gradient across the this cross sectional cross section of the flow, it is important to know that what would be the critical value of a velocity that would be sufficient to keep them suspended. So, the prediction of the critical deposition velocity is very essential while handling this heterogeneous slurries. So, for any heterogeneous slurry, it has to be operated above of this critical deposition velocity. Otherwise, there will be particle settling at the bottom surface of the pipeline. The pumping cost will increase, wear and tear will be in enhanced manner. So, this critical deposition velocity and the consequential pressure drop is dependent on several factors, including the particle size, particle diameter, particle concentration, particle density, and several other terms. So, mostly this deposition velocity and pressure drop are estimated from empirical relations that are derived from a wide set range of experimental data. Now, quite naturally, since these correlations are based on a certain set of data that has been done for a certain range of operating conditions, we have to choose or we have to select the appropriate correlation in order to find these parameters that suits your working condition, or it falls in that range. Otherwise, the calculation would be over predicting or under predicting. And in fact, in most of the cases, this range is not sufficient for the working condition. So, this calculation or this estimation is merely an initial guess or initial value that would help you to have a certain design margin and then go on for the design. So, selection of appropriate correlation is essential for the sound design or sound construction of this pipeline network that will carry this heterogeneous slurries. Now, one of such correlation is shown here, that is from the literature. For the critical deposition velocity is given by this expression, where rho is the solid density, F is the fluid density, this rho F, d is the diameter, g is the gravitational constant. This F is a factor that is dependent on the solids concentration, the volume concentration of solids. So, few researchers have expressed this relation for calculation of F, this factor F. Now, since these are the empirical correlations, and again I mentioned that for a certain range of operation, for a different range of operations, the researchers have revised this and have come up with the other set of expression. So, this is one set, this is another set, this is another expression. So, this one we have seen, and this is the new set of expression for calculating F, which depends on the Archimedes number, which is defined as this. This is the Archimedes number, another dimensionless number. So, here depending on the range of this Archimedes number, the F has been estimated, which goes here to help us calculating the value of critical deposition velocity, above which the operation should be there. But if we look into this expression, or in fact the expression of Archimedes number, it doesn't account for the particle shape or the particle orientation in the slurry. So, that means all these correlations have their limitations, and you have to choose your appropriate correlations based on your working condition, and whichever range or whichever correlation fits you better. So, this is the essence of calculating this critical deposition velocity in heterogeneous slurry. And similarly, there are several pressure drop correlations available. So, if we now briefly look into the other components in the slurry transport, that is what would be there in a slurry flow system. So, basically we started with the concept of slurry, its different types of slurries, that is homogeneous, heterogeneous, and in case of saltation regime which is not desirable, we have not looked into that because that is not a desirable flow regime in a slurry transport. We must avoid that kind of a regime, at least if it happens in heterogeneous regime. So, that is why we have seen the details into the critical deposition velocity above which the slurry should operate, or the operation should be there. Now, once the slurry is moving, what are the other components involved, or how a slurry system in a simplistic manner works? So, it consists of couple of components. One, the vital part is the slurry preparation. After slurry preparation, it is pumped to the pipeline. It goes through the intermediate steps of pump, because if it is a long distance that it has to be flown, then there are intermediate pumps that are required in order to have the consistent pressure. And at the discharge end, once we collect the slurry, we have to recover the solid particles, because that is what we are carrying in terms of slurry. So, the step called dewatering of the slurry, because as I mentioned, most of the cases the slurry is prepared with water as the main component. So, the solid particles are mixed in water and then it is flown. So, this dewatering of this slurry is the final step, and then there is recycle of the carrier liquid, or it can be discharged the waste. So, as I said, slurry preparation is one of the vital component in this case, because the proper characteristics of the slurry has to be there for effective transport. And in order to do that, several physical or the chemical treatments are done. One of the common chemical treatment is the corrosion inhibition of the pipeline. If the materials are abrasive in nature, we have to treat it in proper way. Also, the physical modifications like modification of slurry rheology can be done by the particle size reduction. So, more finer the particles, the slurry becomes homogeneous, and also for a given size, if we increase its concentration, it becomes more homogeneous, which we require ideally. So, if it stays throughout the length as homogeneous slurry, then nothing is settling at the bottom of the pipeline, which is actually desirable. That we want all the solids to be transported from one end to the other end. So, every attempt should be made to create homogeneous slurry, but at the same time the particle size should not be fine enough or finer that the dewatering step becomes difficult, because we have to essentially at this end we have to get this solids back. Now, heterogeneous slurry requires higher pumping and the energy cost, and it would also create a greater pipeline wear if it involves larger particles. So, essentially one of the steps that here involves is that the crushing grinding step of the bigger particles to finer ones. But again, it shouldn't be fine, very fine, so that the dewatering step becomes difficult. Now, the pump selection. So, once slurry is prepared for effective transport, we have to choose appropriate pump that can take that to the desired distance. So, selection of pump for a specific slurry transport line depends on two factors. One is the discharge pressure requirement and the particle characteristics, that is its size, abrasivity, etc. Mostly positive displacement pump and the centrifugal pumps are used. If the discharge pressure is less than 40 bars, 45 bars around this value, then the centrifugal pumps are economic for the application. Now, due to this lower working pressure, centrifugal pumps are applied when there is a shorter distance to travel of this slurry. Efficiency of centrifugal pumps are much lesser than the positive displacement pump. You can get a maximum of efficiency of around 65% in the centrifugal pump, but in the positive displacement pump that can be pushed up to 85 to 90%. Now, this happens due to there is a wide flow passage between the casing and the impellers in centrifugal pump. We will not go into the design details here, but this wide passage also allow very large particles to be pumped in by the centrifugal pumps, that is around 150 millimeter. On the contrary, positive displacement pump can handle a maximum particle size of 2 millimeters. So, you already have a selection criteria there. If the discharge pressure is also greater than 45 bars, then only positive displacement or the reciprocating pumps can be used. That is technically feasible. The other vital component in this slurry flow system is the pipeline material construction or the selection. Since there will be particles, there are particles in the slurry and at very high velocity it is flowing. So, there will be wears on the pipeline inside wall. So, the lining of the pipelines inside wall is also vital. So, sometimes that is done by rubber or rubbery material, also sometimes done it is in ceramic material, but depending on the cost, depending on its abrasivity, resistance to abrasion, this selection becomes important. And this dewatering of slurry at the discharge is the deciding factor whether such kind of slurry transport is effective or not, because eventually if you cannot dewater, then this whole matter of slurry transport shouldn't be there. So, this is the most important parameter that you have to think beforehand before you transport your solid particles in terms of slurry. So, say it is the slurry transport happening, now comes the dewatering step. Now, how the dewatering is done? These are done typically in these three processes that is mentioned here. One is the particle sedimentation by gravity or in a centrifugal field. This we have seen in our previous classes. We have seen also filtration by gravity or in a centrifugal field induced filtration, or that also can be done under pressure or vacuum, and thermal drying of the solution of the slurry. If we evaporate the water, the solid remains. So, in certain slurry or several slurry flow system, all three can be used together or in a sequential manner. So, this brings to the end of this slurry transport phenomena, and in the next lecture we will see the operations involving the fluid phase as the gaseous phase, that is the pneumatic conveying systems. Till then, thank you for your attention.